Let's mess with some polar coordinates. We are going to take this top polar equation, r equals cotangent theta times cosecant theta, and see if we can figure out the rectangular version of that. It looks terrible, but it will turn out to not be so bad. When in doubt, we can always switch everything back to sine and cosine, which is a good idea because our conversion equations between rectangular and polar coordinates involve sine and cosine anyway. So replacing cotangent with cosine over sine and cosecant with 1 over sine, we get this. And then I'm going to cross multiply by sine squared. And get r times sine squared equals cosine theta. Remember that our conversion equations are x equals r cosine theta, y equals r sine theta. So on the left, we might say, oh man, it would be great if this was r squared, because then we'd have r squared sine squared, which would just be y squared. And oh, wouldn't it be great here with cosine to have r times cosine, because then that would just be x. That would be great, right? Well, remember, if you want something, put it there. Just put it there properly. With the goal of making this an r squared, I'm going to multiply both sides of this equation by r. And doing that will just happen to also set us up on the right-hand side correctly. And so now we can combine the polar reworked version of this curve with the conversion equations to replace r sine theta squared. That's just y squared. And then that's equal to r cosine theta, which is equal to x. And so this is the sideways parabola, x equals y squared. Next up, we're going to plot r equals 3 minus 2 cosine theta on this terrible attempt at some polar coordinate markers here. I've drawn measures for theta. You got 0, you got pi over 4, pi over 2, 3 pi over 4, and so on. And these are supposed to be circles of radius 1, 2, 3, and so on. Because, one way to plot this would be to try to convert this to rectangular coordinates, but it wouldn't come out being really instantly recognizable. So we're going to do this the old-fashioned way by just picking some values of theta and seeing what values of r come out and then plotting them. We can pick anything we want for theta, so let's pick some convenient angles, such as 0. When theta is 0, r is going to be 3 minus 2 cosine 0, which is 3 minus 2 times 1, which is 1. And so when theta equals 0, that's this this ray, the x-axis, r is 1. So we're going to put a point at theta equals 0, r equals 1. Then let's sweep around to theta equals pi over 4. Well, when theta equals pi over 4, cosine theta is 1 over the square root of 2. So r is going to be 3 minus 2 times 1 over square root of 2, which is 3 minus the square root of 2, which is 3 minus 1.4-ish. So we're looking at about 1.6. And so on this ray for theta equals pi over 4, we'll put a mark there for that point. When theta is pi over 2, well, there cosine theta is going to be 0, so r is just going to be 3. So 1, 2, 3. And then when theta is 3 pi over 4, this time we're going to get for r 3 minus 2 times. Now the cosine of 3 pi over 4 is negative 1 over the square root of 2. So with a bunch of simplification here, that's 3 plus square root of 2. So now we're at about 4.4-ish. So when we're back here on the ray, corresponding to theta equals 3 pi over 4, we're going to go out a bit more than 4. 1, 2, 3, yeah, so we're about there. And then I think by the time we do theta equals pi, maybe we'll know enough. This will be 3 minus 2 cosine pi, which is 3 minus 2 times negative 1. Or 3 plus 2, that's 5. So right back there at theta equals pi, r equals 5. Now, it turns out that because of symmetry, if we were to do theta equals negative pi over 4, negative pi over 2, we'd get just the opposite, or we'd get, sorry, the same things for all these radius values. So maybe right there, and then right about there. And then what about 1, 2, 3, here about there. So I've tried my best to make them similar, and then we just play connect the dots. There's a little bit of a dip right in there. I've made it, that's not supposed to be a sharp corner. I'm just bad at rounding myself there. But it's a little bit of a, a cusp and then a fatter end to the left, kind of like an apple, perhaps, or a tomato. Maybe if we put a little doodle on the top there, now it's a tomato.